Hi everyone, and welcome to the Kotlin London Meetup. In our third online meetup, we're getting better organizers and streamers, and we're also growing our community. Now we have more than 1,300 members on our meetup, and more than 100 subscribers, which is a milestone we want to achieve as soon as possible here on YouTube, of course. And we have our first two events that are more than 800 views, and really hoping to have like a 1,000 views as soon as possible. As promised, we're trying to give new talks, new content every month, and keeping the momentum. Doing online events let us also to have speakers from all over the globe. We'll see for our speakers in a while, and this is also helping to expand our community. So if you haven't done it yet, join the Meetup page, hit subscribe to our YouTube channel, and follow us on Twitter. But also speak to your friends and colleagues who might be interested in watching the Kotlin talks, but also giving Kotlin talks. We're also looking for new speakers. One example is one of our speakers tonight, Garth Gilmour, who introduced us into the British and Irish Kotlin user group organizers. So we can share speakers, info on the upcoming events. As usual, we have two talks tonight. The first one is from Moore and Nicolás D'Cotta. They're speaking on adding pattern matching to Kotlin. Second one, as I said, is from Garth Gilmour. We'll talk about generics on JVM. What you don't know will hurt you. So we would like to thank them to accepting to speak to our meetup. Just remember that the QA will be done after each talk, and the link for the questions in the description of the event here on YouTube. During or after the talks, please give a small feedback, just a clap or just a thumbs up. It's really, really important for the speaker to have a small feedback to understand that you're watching, that you're appreciating what they're doing. So yeah, I think that's it for me. So I'll pass it to our first two speakers, Moore and Nicolás. Thank you.
Hi, I'm Nico. We're going to talk today, me and Matt, about adding pattern matching to Kotlin. So, tiny bit about me. I am a student at Imperial College London. I just started working on my second startup, blockchain.com, also based in London. So in this talk, feel free to stop, feel free to send a message if I'm going too quickly. As you should know, there's a slight stream and a delay, but again, I have no feedback with my colleagues. So I will assume no knowledge of pattern matching. So if you've never heard of it, I think this is actually a good place to start. And well, let's jump right into it. So if you're developers in Kotlin, you might have come across code like this. So there's a few problems with this, and you do not need to understand everything that's going on. But here are the main takeaways. We have a really big when clause, and it has nested branching. In particular, it has 4 branches, but actually 1, 2, 3, 4, 5 cases, 3 branches in 5 cases. So the problem here is we have duplicate branches and a lot of nested constructs. In particular, we have a nested when and 2 nested ifs. And all we actually want to do here is just, we have some data and we're looking to see if it fits a model we expect, i.e., does this data look this way? And if so, can I do something accordingly? So this is just branching, and we do this all the time in programming. And turns out there is a very popular construct that exists in other languages. that allows us to inspect data and just branch out depending on that. So in Kotlin, we do this most of the time thanks to when, if, and sometimes polymorphism. And if we applied pattern matching to Kotlin, potentially it could look like this. There was a lot going on the other slide, and this is supposedly exactly the same thing. So I'm going to really slowly go through what is going on here so you can get an idea of all the stuff that potentially could be added to the language. So let's start with the stuff we know. Here we're looking at just a regular when clause. We're checking whether our download, which remember could be either an app or a movie, is either of both. And if you inspect the seal class, both have a name, a title, and then an app may have a developer, which may be a person or not. So here we check if our download is an app, and that's the usual type check. And then we can destructure. So this would work pretty much the same way it already works in Kotlin. We can just depend on our extension functions, component 1 and component 2, to look at the values inside our download. So here we are calling component 1 in the download. So this is, again, it's hypothetical. This is not valid Kotlin, as you know, but we're exploring the possibility of how it would be if this was a valid Kotlin. This is where it gets fun, because here we just destructured our first component, but here we can do a type check on the second component. So this is a recursive check. So the same thing we were doing with our download and the type check of an app, we are doing with a download component 2 and a type check of a person. So here we are checking the developer. So is our developer a person? Then again, we can carry on destructuring. We don't care about this bit, so we can just use a wildcard. And here, an equality match happens, so not a type check. So again, this was a destructure. So this is component 1 of our developer, and we're just checking whether the name matches Alice. So based on all this, from one line, we know our download is an app. It was developed by Alice, and Alice is a person. Additionally, we extracted name, which is just the name of the app. And so we have a branch. And then the next branch is exactly the same. And the third bit is also interesting, because here we have a fallback. And it's a fallback where we have exhaustiveness. i.e., if a download is either an app or a movie, this is covered. And since it is a seal class, it can only be an app or a movie, right? Therefore, if Alice was to write a book, we would not be able to miss it. So the way pattern matching works is we check this pattern, does it match? No, we check the next, does it match? Then we check the next. And note how all duplicate branches before are now a single branch. So if this was some complex error, we would only have to do it once. Now, this is nice. We did type checking, we did equality checking, we destructured, but there are some more things we'd like to do. Ideally, we'd like to match on anything, not just like equality or just a type. So for that, we'd like more constraints. So take a look at this example. This I borrowed from the code base of TornadoFX. So it's actual code just running in real life. A lot of you might have used it. So what goes on here is the same thing as before. We have a when, nested if, and we have two cases. So if we were pattern matching here, what we would ideally want is have one entry for a JSON array that is empty and an entry for a JSON array that is not empty. But instead, we are forced to have a single entry for a JSON array and then inside do an additional check. So what we could use is something called a guard. A guard is a construct that allows us to guard against the match, i.e. it protects the match. So in here, we check if it's a JSON array. If it's a JSON array and it is empty, then we can go carry on with this branch. And otherwise, we can carry on through this branch. So note how this actually looks a lot like what we had before. How is this not a nested if, right? So that is an interesting question, and we'll come back to that in a bit. But otherwise, you see the rest of the cases are the same, because in this example, we do not really care about equality. We only care about the type of what we're checking in. And in this case, whether it's empty or not. So note how this is a smart cast as well. We can only check whether an array is empty. We cannot check whether a JSON element is empty. So that was also nice, but when we code, it's not always that nice. Why? Well, we don't always deal with data classes. We don't always deal with the structuring we know. In particular, with regards to the first example, we're using data classes. They have component 1, component 2 functions, and it's a sealed class. That's not always the case. So take this example. A lot of going on. You don't need to stop to think about all of it. But the main takeaway is that we're checking a class that is not ours. So this is an actual class from AWS Lambda. It's a library. It's a Java library. And as Kotlin developers, we often have to actually deal with Java libraries. So this is code we had to write. What we're aiming to do is just route requests that come to us as this input parameter. And we want just to call functions on them depending on how they look like, right? So for example, take the first one. When our path is invites and the method is get, just create an invite, right? Just because we just getting the invite. Anyway, what's the problem with this thing? So again, nested whens and repeated paths. And we'd like to destructure on it, but this is not a data class. But good thing, destructuring actually comes with component end functions. So what we can do is just define extension functions, which most of you know, I'm sure, and match in a class that is not Java, that is not Kotlin. So what is this? This is just another pattern match, and we extensively use guards to check on the method. So this is where this example is really different from nested ifs, because we don't have an else clause after an if statement. And this is fundamentally different from the if-else expression in the Kotlin language as it is now, in that when you write if as an expression, you are forced to write an else. This does not happen in pattern matching. These are cases, and they're checked one by one. And if one doesn't match, you just carry on to the next, whether it's a guard or not. So here we check for our API gateway proxy request event, which we know to be true because we're checking on that. We destructure a quality check on the path, extract the method, extract the body, check whether the method is equal to either get or post, and then call functions accordingly. And if it's not equal to either, we can carry on and match against a different path. Whereas if we were using nested ifs or nested whens, we would be forced to handle the case where the method doesn't match here. But that's not happening here. Here, it falls back to this one, which also won't match. So we will fall back to this one, so we can fall back to our error. So here we have a single path to handle our fallback case. So you might have noticed that we know the type of an API gateway proxy request event. So why would we need to type check an API gateway proxy request event? The short answer is we really don't. So we could just skip that type and just leave a wildcard. And the wildcard itself could be omitted as well, since we're only interested in the destructuring and the equality check. So this is when the when clause starts looking really different from what you're used to, because we're not even doing a type check. We're doing a pattern match where we don't care about the type. So we decided to omit the type. But we still get all the other benefits. We're just typing less stuff. So that was pretty much it. That's pretty much the idea that I currently have of what pattern matching in Kotlin could look like. But we should compare that to the state of the art in other languages. In particular, functional languages have done pattern matching really well for years now. And it's just a really popular feature. It's tried and tested, and it's very idiomatic. So how would that compare? Well, let's take a look at this example. So this is still Kotlin. We have a simple CL class. It's just an option. It's either some int or nothing. And through guards, we're just checking what the int looks like, if it's there, and if it's not there, just a different message. So we have 4 cases here. And here we're doing it with 2 matches and 3 guards. And we'll just 2 guards on the else case. So Scala does it very similarly. You could read Kotlin, you could still read this. We're just matching on result and extracting X from each of the matches. So Scala has guards, but it only has one at a time. Whereas here we could kind of chain the guards and not have to rewrite some every time. Still very readable for cases. This is Haskell. So I'll go really quickly over it because Haskell is very different in syntax from JVM languages or C-like languages. But this is the same we had before. This is a match. We're matching on something. And this is guard. So this means if, and this means otherwise, as you can read. So again, not much to say here. When we evaluate this with sum3, we'll get the case we expect. And Java. So some of you might be surprised to see Java in this comparison, but Java is actually considering adding pattern matching. And if you've used JVM, so the Java 15, you've seen a really early preview of this, which is pattern matching in instance of, in if-else. So eventually there's several proposals, draft of GEP proposals, where pattern matching could be added to the language. And this particular example is taken from Brian Goitz's blog. And he wrote several of this, pretty much all of these drafts. So if you've used Java, you can read this. And this is what a switch case, a switch expression with pattern matching could look like in, say, Java 15, 16, or 17. And the drafts also mention adding guards. So in practice, the Kotlin pattern matching we just imagined could become reality in Java in some years and is actually on its track for that to be the case. So this was nice. We kind of managed to be on par with existing solutions that are really popular, and they're just tried and tested, except the Java one, and have been there for several years. In Haskell, it's the way to do control flow. But can we do better? So can we be more original than this? Can we come up with nicer stuff that maybe fits better into Kotlin than just the already popular idea? So there's several possibilities for this. First off, the syntax that you've seen, you should not stick to it too much. I just wanted to discuss the idea and the semantics of a possible pattern match. So could the syntax look more nicely? We always like good syntax. Can we have nicer guards, like maybe have guards as a function of lambdas and compose them, like we could compose functions? How do we destructure a data class with 10 fields? You can imagine what that would look like. We just have to like add wildcards for every single one of the fields. So in particular, Scala is kind of having this problem. Could we match outside of a when expression? Like, why not match in an if? So all these questions, well, we have to agree on them. And all of this is up to debate. This and all we've discussed so far, there's room for improvement. So how do we add all of this idea? How do we add it to the language? How do we get pattern matching in Kotlin? So one way is to ask nicely and submit a request, a keep. So I wrote keep 213 a few weeks ago, where I discuss all of the slides I just showed you and some alternatives and extensions. And I hope at some point the Kotlin team will consider adding it to the language. So if you haven't seen it yet, go take a look if you have enjoyed the talk I just gave. It has several real-world code examples where it shows how pattern matching could benefit the code base. It has some possibilities, some syntax alternatives. So if you like this idea and you'd like to see more of it, you're welcome to take a look, comment, leave feedback. You like it, say so. You don't like it, say so. But there's another way of adding pattern matching to the language, is making it ourselves, if the Kotlin team is not up for it. So I hope you enjoyed the talk. And now we're going to talk, Matt, my friend, is going to talk to you about how we could just bake it into the language. Thank you.
So yeah, we're going to talk today about doing this as a compiler plugin, and going to actually share my slides as well. All right, I'm going to start with a little quick story time here. when I started this whole process, I knew some things about compilers, but I was not an expert of the Kotlin compiler. So my story on this was discovering Nico's Keep, which I was very excited about, and I wanted to make this possible. As he mentioned, the Keep is the sort of nice way of asking, but we wanted to experiment with this as early as possible. And so after conversations with Nico and Rahul Raja at 47 Degrees and a few others, thank you for your help, we kind of decided, let's bring this into Arrow Meta and start it as a compiler plugin. And the nice thing about that is you guys can start experimenting with that during this year as we're working through it and getting it ready. I also wanted to just point out that if you're not familiar with the compiler, and there's not a lot of documentation out there on this, so it can be tough, please do join the Kotlin Link Slack and ask questions. People are very friendly there, and that really helped me trying to figure this out as I started. Not a compiler expert, limited information. There's almost nothing you try to Google on this stuff, you're not going to find it. Equals help. So please do reach out for help on Kotlin Link. All right, so why a compiler plugin, and why are we not doing this directly in Kotlin? Again, as Nico mentioned, trying to get this in the compiler is going to be kind of a long process, right? When you add features to a language, you need to get buy-in from the community. And there's a lot of folks in the Kotlin community who are very interested in this and have been for a while. But some folks maybe don't feel comfortable with it right away. You need to make sure that language feature fits in with the rest of the syntax and the semantics of the language. And we'll discuss how that looks with the underscore for the wildcard matching as Nico had shown you. So doing this as a compiler plugin allows us to kind of experiment with what syntax looks right, what semantics work right. I actually see there's a question here, which I'm going to just quickly address. If you define component extension functions on a class that is already defined as a data class, will the compiler use the most local definitions? The answer to the question is we don't yet know. This is something we could do, and I'm actually really happy that you posted that question, because I encourage people to post questions on this. We want to try to figure out what you and the community actually want to see with this new feature that we're bringing to the language, what makes sense with scoping and other questions like that. Arrow Meta, I want to talk about this for a little bit. You can build compiler plugins without Arrow Meta if you want to use the internal compiler APIs. The nice thing about Arrow Meta is that it provides us with a lot of features out of the box, thanks to the work that Rahul Raj and others have done over there at 47 Degrees. Features that make building compiler plugins just that much easier. And so Arrow Meta just made perfect sense in this case. We're actually hosting the current code for this in Arrow Meta at present. Also, you would get inclusion in the Arrow ecosystem. So if you are already planning to use Arrow Meta, you could just automatically out of the box get access to pattern matching as part of that, rather than having to go install yet another compiler plugin. The other nice thing about using Arrow Meta is there's advanced type features in there. Roland and Simon have been working on a lot of interesting features around type proofs. And some of those things would become useful for us to enable us to automatically have access to things down the road outside of the box. So overall, Arrow Meta was just kind of the perfect fit for what we were trying to do with this. So let's talk about the plugin itself. The plugin, sort of at its core, is broken down into these four main steps that we're doing. We have here enable IR. Now, IR, for those not familiar, is intermediate representation. And basically what this is in the Kotlin compiler, especially as we move into version 1.4, we're going to start seeing some changes in the compiler where instead of just directly using ASM, which is what's typically used to generate Java bytecode, we're going to have this layer between code generation. Code generation would be the stage where you actually get your bytecode for whatever target you're targeting, whether it be the JVM or native, anything like that. So IR sort of helps make that process a little bit easier, and it is the future moving forward. Consequently, in this plugin, we actually want to turn that on. Now, the plugin's running on version 1.3, 0.61, I believe, currently, of the language, which we're currently restricted to that within AeroMeta because of changes that we're waiting for in 1.4, which, from what I understand, should be coming out soon. So we turn IR on, and that lets us do a little more interesting things. The next step is, we're dealing with pattern matching. We've got these different symbols we're going to add. So we have underscore here in this case. The underscore does represent a wildcard, as seen in Scala. And if you just stick that into your IntelliJ, you'll notice that it's going to show up as an error for pattern matching because it's not yet defined. And that's, of course, what this plugin is doing, is defining what that means. So we need a way to suppress that error. Any of the errors that come up from this these new semantics that we're going to add in for this syntax. The next stage, of course, is the analysis phase. The analysis phase is interesting because that's where a lot of the deeper stuff takes place, with things like type checking, resolving the expressions, so the underscore as an expression. So that's a piece that we're spending a lot of time on to try to figure out the best ways to handle those things. And then finally, once we get past the analysis phase, we have the IR tree transform. So again, once we've gone through this whole process, after we've enabled IR and we've gone through the rest of the process of type checking and everything else, the IR tree, we may need to also make changes. So that basically means we'd be rewriting the tree structures that the when expression, for example, would output into forms that we could, that the rest of the compiler could understand as it generates bytecode. So that's the basic overview. Let's take a look here at one of the issues we ran into when doing this. So the underscore in this case, as this is a sort of shortened version of what Nico is showing you. The underscore in this case is difficult because underscore in Kotlin, of course, represents unused parameters, and we need a way to separate that out, right? We don't want to collide or clash with Kotlin's existing underscore semantics. So we needed a way to actually separate that out and say, this is marked off as our underscore for pattern matching, but don't affect anything else. And one way we did this is, if you look here, we have the case keyword, which I'll make larger here. It's a function. And that's a way to actually separate that off and mark it out so we know what that's for. So case is you might be wondering where it's coming from. It is a new function that we've added in the plugin. And it literally just, in fact, I believe I have an example here. Yes, we're calling it a synthetic function. Basically, it's a function that really does nothing. It just takes a parameter in of any nullable type, and it returns any nullable type. And you can see here, it just equals arg. That's it. It's literally just a way to mark off, hey, everything in these parentheses should be interpreted as pattern matching in the semantics. Here you'll notice when trying to look at using case, we had some issues with the parser. The interesting thing with a plugin for a compiler is you can't modify like all of the syntax, right? You're still stuck with what the parser understands as valid syntax. But we're trying to rearrange that. And so one of the first things we tried was taking this case keyword and putting that in without the parentheses. And of course, you'll notice over here on the right, this is a PSI viewer, which has been very helpful in figuring this out. We start getting all kinds of errors out of this. We can't parse these things correctly. So that didn't really work. And of course, the answer was to just move to turning this into a synthetic function. And as you'll notice here, the difference between these two, we go from errors to now it's cleanly parsing at least. So yeah, that clears up the underscore as a reserved keyword. It also safeguards and protects it for our use case, while not affecting Kotlin's existing semantics. The other issue we run into here is suppressing warnings for the underscore. So the compiler will throw an unresolved reference. Let's say we got case, that's matching fine. We've got the underscore now sitting in there, but the underscore does throw that error. It doesn't know what underscore means yet. And before we even get to the point where we can start defining what underscore means, we had to actually alter what it refers to and change its type. If looking at the underscore, we notice that it has a null type, which is useful because it's a way for us to also further ensure that we're not clashing with the existing underscore semantics in Kotlin. So that combined with case, that was enough for us to determine that this is our case to modify. So the first stage of this, once we've gotten those errors suppressed, is to start resolving type information. This happens during what's called the analysis phase, as I mentioned earlier. So we can go in there and we can check on the expression underscore when it comes through, and we can actually verify, yeah, the type is null. We can backtrack in the tree to see whether or not it's wrapped inside a case, just to further restrict that down. Once we've gotten that, we've found those elements for underscore, we can then record in the analysis phase what the type of the expression is. So if underscore refers to like first name, which is a string, we would record that underscore in this case should be a string. And then the next step after we get the type information recorded is we want to record the actual the reference that it would refer to. For example, this is where the destructuring with component one, component n, etc., would be used. We can say this is going to be a function that looks up some property of a class. All of this information is something we can do through binding trace and binding context. These are these are calls that we can use. With binding trace, we can get all the information we need at compile time to look up things through the tree. And then we can use the binding context to actually write those expressions, all the type checking and everything. That goes back through the binding context. And just to kind of give you a little overview here, this is the code at the high level for the pattern matching plugin. Is not very big. It's a little bit misleading because some of these functions, in particular down here, resolve pattern expression and the wildcards function that we pass in there. There's actually a bit of code going on behind that. But in a nutshell, I just wanted to show you that this is actually not that hard to do this at the high level. Here we have analysis phase. We're enabling IR, as I mentioned, as our first step, suppressing diagnostic. We're getting rid of those unresolved reference exceptions for underscore. And then we proceed with the type checking process that we need to go through and resolve those expressions. So it's actually not that hard to throw together a plugin in this fashion. The real question is, does it work? I've been talking about all this stuff, and that's great, but let's have some evidence that this is actually going to work. Let's find out. I'm going to do a little demo. So I'm going to switch over here to screen share my IntelliJ instance. All right, so here we are. You'll notice I have the case synthetic function in here. We don't at present actually have that being auto-written by the compiler at compile time. So I've inserted that in here for the time being. However, we do have this case with the actual wildcard in here that I mentioned. And we are pulling the first name on the match, and we're going to return that. And then let's print the result. So let's actually see if this works. I hit run up here, and it works. It prints my name. So that's about all we have working right now. It's still heavily a work in progress, and we can switch that, by the way. We can do underscore on the first name, last name. Either case works at present. Some of the more advanced stuff around nesting and guards. We don't have guards yet included. So we still have to figure that part out, but it is in fact working. So I just wanted to, again, give a special thanks to all the folks who have really gotten this kicked off with us. Raul Raja, of course. Nico, thank you. Andre, and I don't know if I'm pronouncing your last name correctly, but Shaikov, I hope I'm saying that right. He's been indispensable in understanding some of the compiler internals with the expressions and how to do some of the type recording. So, and many others have helped us. Really do appreciate it. If you want more information on this, here's the Keep, which Nico had already told you about. Our pull request is up on Arrow Meta, so feel free to check that out. It's PR 651. We're on kotlinx Slack at the pattern matching channel. And there's Nico and my GitHub and various handles. So that's about all I have, folks. I hope you find this interesting. I hope you follow along with us. And please do share and let us know what you think.
Thanks, Matt. Thanks, Nico. We have one question. I'm not sure if you can see it.
Should I answer?
Well, yeah. If you want.
So
go for it.
We are aware pattern matching was discussed, and like you say, it was pretty much avoided. So the remark, I just watched the clip, good thing that you sent it. The remark that was done is that it is a difficult question, and there was a bit conditional, which is if Java ever ships it. So a year and a bit later, we are seeing Java is completely on track to actually ship pattern matching. So the conditional is there, and there hasn't ever been like a proper discussion about it. So there has been no keep. So if pattern matching gets thrown away, that's completely fine. That's completely fine. But that should not happen before having a discussion about the possibility of it and all the ways it could come about and what shape it could take. Maybe we're just imagining it the wrong way and we're just waiting to someone to come along and just come up with a proper way of doing it.
Yeah, not much to add to that. Exactly. I just back up what Nico said. This is kind of a learning experience for us to figure out how to do this the right way for the community. And again, to echo what Nico said, please join in on the Keep and throw your suggestions or thoughts in there, because that helps us figure this out too. So.
Thanks again, Matt and Nico. Thanks so much. We now switch it to our second speaker. Just like 30 seconds of transition, we can set up everything. And we go with Garth Gilmour. We talk about generics on the JVM. What you don't know will hurt you.
Hi, everybody. This is the second talk of the evening. So this is generics on the Java virtual machine. What you don't know will most definitely hurt you. So just get my slides sorted out. Here we are. So my name's Garth Gilmour. I was a full-time software developer for about 6 years. And then the opportunity came up to give this a go. And terrifyingly, that was in 2001. So back of an envelope, I've done about 1,000 different workshops and training courses and conferences and all that kind of thing. And I'm the head of learning, the chief trainer for a company called Instill. We're based out of Belfast. So about 80% of what we do is software development, but we also do consultancy and training as well. And the consultancy and training wing is louder than the rest of the company. So that's how most people encounter us for the first time. And these are a bunch of people that we've worked for. So a quick shout out before we begin. We run a user group in Belfast called Bash. In the beginning, it was just Bash. And then people started saying, Belfast Association of Software Hipsters. And we went, yeah, that's what we always meant. Really good. So once a month, we pick a topic in computer science and we have 2 or 3 really good speakers. So we're doing those virtually now. They're online. They're worth a look. And we also host the Belfast Kotlin user group. So if you're interested in presenting there, just let us know. You'd be very welcome. So the agenda for this talk, it's really generics in 3 acts. So in the first act, we'll make clear the existing issues in Java. In the second act, how Kotlin simplifies these and mitigates against them even. And then in Act 3, some of the fun things that await us. Some of the fun ways that generics could be extended on the JVM for all JVM-based languages. So let's start out with a definition, always a good idea. What's generics? Well, this is from a tremendously good presentation by Ted Neward on advanced stuff that you can do with TypeScript. So if you have any interest in TypeScript at all, really great talk. And I love his definition. Generics are those things that hurt people. Okay, so why should generics be so bad? Well, continuing with his talk, it's extremely hard to debug a type system. In other words, we can write regular code and we can attach a debugger to it and step through it and so on. But whenever you're working with generics, there's stuff going on at compile time. So things are being understood and mapped and transformed and so on. And we have to kind of mentally visualize what's going on inside the compiler. And it's not really something that you can debug into. So that makes generics particularly hard. So as you know, of course, in the beginning, Java and C# lacked generics. You could still do generic coding with a lowercase g through using references of type object, but that didn't really give you type safety. So they added it to both languages, but they went off in different directions. And they were both right, yeah, because in the case of C#, it was a relatively new language, and they weren't too worried about breaking backwards compatibility. In the case of Java, it was a much more mature language. They had billions of lines of code out there. So the last thing they wanted to do was break backwards compatibility. So they went different ways, but they were both right, that they were both following the correct path. So whenever they added generics to Java, it was first prototyped through a language called Pizza. Yeah, and Martin Odersky was the main person there, who of course then went on to develop Scala. So if you're not familiar with Pizza, it's well worth your time. So I would refer to you this tremendously good talk from GoTo Copenhagen back in 2019, which goes into detail about how Pizza prototyped many of the features that we now enjoy in Java and Kotlin and Scala and so on, and even some features that are still to come. So a brilliant talk, well worth your time. And then just in terms of background reading, so white paper, I always recommend Generics in the Java Programming Language by Gilad Bracha. That came out in 2004, just before Java 1.5, just before they added generics to the language. Really good paper. And then another one by Brian Getz from this month, so really, really good paper again discussing why they went the way they went with generics. And then if you really want to get into it, as maintained by Angelica Langer, there's the Java Generics FAQ, which comes in, last I checked, at over 350 pages. Yeah, so you're not going to get through that in a single evening. Okay, so that's something that you just want to dip into. But the sheer size of that should give us some idea of the complexity. So, Act 1, let's just explain where the complexity comes from. So we'll take the class hierarchy that everybody uses. We'll have director extends manager and manager extends employee, and let's have 3 linked lists. So we won't bother about interfaces. We won't use lots of collections. We'll just pick one concrete type, and that's the linked list type. So emp list is going to be a linked list of employee, manager list, linked list of manager, dir list, linked list of director. And let's say we've got this function here, Q1, and we're passing in a linked list of employee. And we've got these 3 calls here, A, B, and C. So A, we're passing in the emp list, B, the manager list, C, the director list. Yeah. So if you ask a bunch of Java or Kotlin developers without them knowing it's a trap, which of these will work, they'll say all of them. Yeah. But of course, if you've played with this before, you'll know that only A will work. Okay, and what's the reason for that? Yeah, well, because inside Q1, we might want to add an employee. Makes sense. It's a linked list of employees. So to a linked list of employee, we'd like to be able to add an employee. But note that if we let calls B or C go through, yeah, well, then we'd be adding an employee to a linked list of manager. We'd be adding an employee to a linked list of director. So we don't want to be able to do that. Okay, so it turns out that only call A is allowed to go through. But then if we look at this code here and say, okay, so let's say we call this function here Q2 and pass in a linked list of employee, what will we be allowed to add to it? So again, most people, having seen the one before, they'll go, aha, only an employee. Yeah, but it turns out that all of these will work. Okay, and why would all of these work? Well, because it's a linked list of nodes, and each node contains a reference of type employee. Okay, so this is Java, and we're working with reference types. Objects are always accessed through references, and you have the apparent type of the reference versus the inherent type of the object. So the reference can be of type employee, but the object can be of type manager, and so on. And that I find is really the problem with generics, okay? So the problem with generics is not understanding type parameters themselves. The problem with generics is that in Java or Kotlin or Scala or whatever language you're working with, you're juggling the rules of type parameters, and you're juggling the rules for inheritance and object orientation, and you're juggling the rules for reference types, okay? So if you like, there's 3 balls in the air, and you have to keep juggling them, yeah? And sometimes your intuitions in one direction will send you the wrong way, yeah? So your OO intuitions, yeah, can send you badly in the wrong direction whenever you're thinking about type parameters and so on, yeah? So it can be incredibly difficult to juggle these things at the same time. There's a lot of cognitive dissonance, there's a lot of interference that goes on. So that's what makes generics particularly hard. So going back to our questions, looking at this code here, which of these will work? Well, here we're using the wildcard, okay? We're using the question mark, and all of these calls will go through. Yay, okay? But then the problem is, what happens if we try to add anything? We won't be allowed to, okay? So we can pass in a linked list of anything, but we won't be allowed to add any kind of object. We won't even be allowed to add, call D there, a new object. That trips up an awful lot of people. A lot of people think that should be possible, but it's not. So the reason why all of those fail is that the question mark doesn't mean anything works. The question mark means of unknown type, okay? So we're saying to the compiler, please willfully forget everything you know about this type. So because we're forgetting what we know about the type, we won't be allowed to add anything at all, yeah? And again, people internalize the wrong rule. So a reference of type object can point to anything, but that doesn't mean an instance of the object type is acceptable everywhere, okay? That's a subtle distinction that can trip people up, okay? So yes, a reference of type object can point to anything, but that does not mean that an instance of the object type is acceptable everywhere. So that's another common trap that people fall into. So that's not the complicated stuff. That's the prelude, okay? So where the wheels really start falling off the cart is whenever you start getting into the bounded wildcards, okay? So you see here, we can say question mark extends manager, yeah? So T is either manager or something that extends manager. So in this case, calls B and C, they should proceed, they should go through. And then if we try and add something, well, because we've said T is manager or something that extends manager, you'd think that we could say new manager or new director, but we can't, okay? And it turns out that all of these fail. And this was the really big thing that stumped me whenever I was personally learning generics. And it wasn't until I read a tutorial where they said, look, the set of possible values for T here is actually infinite. In other words, if I wanted to, I could devote the rest of my life to creating classes which extend from manager or director, okay? Wouldn't be a particularly good life, but I could do it, okay? So let's say after we write Q6, I go out and create classes like CTO and CEO, which extend from director, and then I can call Q6 and pass in, for example, a linked list of CTO, So to a linked list of CTO, I shouldn't be adding a regular director. Okay, so because the possible set of values of T is infinite, I'm not allowed to add anything. Now we could go the other way. We could say question mark super manager. Yeah, so now T is either manager or employee or object. Okay, so if we do that, then A and B will go through, and we know for sure there are 3 possibilities for T. And that will mean that we can add things, okay? So it kind of confuses people that we can add things, especially that we can add a director. But if you think about it, what are the possible circumstances that we could have, okay? What are the possible values for T? Well, we know that T is either manager, employee, or object. So can a reference of type object point to a director? Yes. Can a reference of type employee point to a director? Yes. Can a reference of type manager point to a director? Yes. So we're all good. Yeah. So for all three possible values of T, it'll work. So we can allow the adding of a director to the linked list. So just thinking about what we've learned so far, yeah, generics and inheritance hate each other. Okay, that's the big lesson I'm trying to get across. Okay, so generics, grand. OO, grand, until you include inheritance. So once you start mixing generics and inheritance together, it all gets very complicated. And our OO instincts will send us the wrong way a lot of the time with generics, and everybody finds these bounded wildcards confusing. They don't work the way we want, okay? It also doesn't help that you've got three kinds of terminology, okay? So we're saying extends, but that's an upper bounded wildcard, okay? So extends means upper, yeah? So how do you get used to that? Well, the way I like to think about it is that assuming you draw inheritance trees the way most people do, with the base at the top and the derived underneath, well, whatever T is, you go up to go to manager, or you stay the same. And then if you use super, well, that's a lower bounded wildcard. And the way I memorize that is that you go down to get from whatever T is to manager, or stay the same, okay? So just while we're talking about, this, as an educationalist, as somebody who teaches people, the or stay the same bit causes no end of confusion, okay? So we do have language designers on the call. This is great, yeah? So please let me appeal to you, do not repurpose keywords, okay? No good ever comes of it, yeah? So we had a wonderful example of this the other day. In C++, whenever they were doing generics, they needed a keyword to introduce a type parameter. So you can't just say T or U, yeah? So what they did initially was they repurposed class. So if you've done C++, you'll know that one way you can introduce a type parameter is by saying class T. Don't, okay? So that they did this initially, and it confused the hell out of everybody. So much so that they introduced a new keyword type name, and that's what you're supposed to use. But as you can see from this little Twitter poll, which went out a few days ago, even now, 20 years after they've done it, almost 13% still prefer to say class T. So this was my comment here at the top. Please don't do this, okay? This will confuse the hell out of students, yeah? And you can see below, this gentleman here very kindly backed me up, it causes nothing but confusion. So please, whenever you're designing or extending a programming language, don't repurpose keywords. It's a very, very bad idea. So we've said that you can say extends, and that means upper, and you can say super, and that means lower. But then we get the computer science terminology, because the wonderful thing about standards is there's so many to choose from. Yeah. So if you're using the upper bounded wildcard, that means covariance. If you're using the lower bounded wildcard, that means contravariance. Yeah. So if something's covariant, then we can extract. If something's contravariant, we can insert. And people are forever coming up with little diagrams. Here's a particularly nice one here to try and explain what that means, but it confuses everybody. So in the world of Java, there is this rule here from Joshua Bloch, which doesn't really do it for me. I still find this confusing, but it is a good rule. So producer extends, consumer super. What? In other words, think about it from the collection's point of view, okay? If you're a collection and you're being referenced, and the type of that reference is a bounded wildcard that uses extends, well, then you can produce, yeah? You can send stuff back. On the other hand, if the reference is a bounded wildcard that uses super, well, then you can consume, okay? Things can be passed into you. So that's one way of thinking about it. A better way, which I really like, comes from Anders Hejelsberg, sorry for massacring his name there, who invented C# and TypeScript, amongst many, many other things. And again, there was a little competition on Twitter, and the competition was, what's the most difficult programming concept you can explain in a tweet? And this, for me, is gold. This is absolutely brilliant. So he says, okay, let's say you've got a type variable, and it's typing something which is read-only. It's naturally covariant. You can get stuff out, okay? But when a type variable types something which is write-only, it's naturally contravariant. You can put stuff in, yeah? But then when it's both read and write, well, then it's naturally invariant. The type has to be exact. So that really summed it up nicely for me. And then the final thing, before we leave Java behind, can I do this? No, sadly not. I cannot create a new T. Or you see here, we're trying to create a static field of type T and an instance field of type T. Can I do these? Well, only one. Which one? B. I can only do B. And that's because generics on the JVM is non-reified. Okay, so again, what does that mean? Well, this is the other thing that you need to understand if you're going to make sense of generics on the JVM. So non-reified means that it's compile time only. In other words, the information that you're providing using the type parameters is used by the compiler and then erased. So I'm sure you're all familiar with the term, pardon me, type erasure. So you use T, but T usually gets replaced with object, unless you've used an upper bound, in which in this case it would get replaced with employee and so on. So another way in which it's phrased is that you've got two kinds of translation. You've got a homogeneous translation and a heterogeneous translation. So homogeneous is what you have in Java, okay? So that's where no matter what values you've given to T and how many different values you've used for T, you only get one output, okay? The other way of doing it, reified generics, is where you get a different version of the class for each use of T. So let's say we had a linked list of employee, yeah, well then the compiler would basically generate an employee linked list. You know, it would go through your code and each instance of T would get replaced with employee. And then let's say you also had a linked list of manager. Well, then it would go through your code and each instance of T would get replaced with manager. So effectively you'd have a manager linked list. And the same thing for director, you know. So if in your code you had said linked list employee, linked list manager, linked list director, well, then at runtime, what you would have is three specializations, you know, three different versions of the class. So the compiler and the virtual machine would in some way collaborate so that if you had 3 versions of T or 5 versions of T or n values for T, well, you get n different versions of the class at runtime, okay? And that's what reified generics means. So, of course, you don't get that for free. For example, in C++, it swells the size of your output, you know. So if you've used the standard collections and you've used a lot of different values of T and it's a relatively small program, well, you look at the size of your executable and you go, whoa, why is that .exe so massive, you know? And that's because for every different value of T, a new version of the class actually got created. So was it a good idea to go the Java way? You know, was it a good idea for things to be non-reified and types to be erased and so on? Well, in that white paper I recommended earlier, Brian Getz makes a very strong and persuasive case for it being the right way to go. You know, that erasure and the JVM is a good way to go. And he says, look, you know, erasure in general is something that compilers do all the time, because you're going from a higher level format, the Java language, to a lower level format like assembly or bytecode or whatever. So certain abstractions get erased along the way. That's just how it works, you know? And I accept absolutely everything he says and still disagree, okay? Because I'm an educator. I only care about how hard or simple it is to teach people, yeah? And the problem is that we're not just going down, we're also going back up again, okay? So whether you're using Scala, or Kotlin or Java, well, yes, you're compiling to bytecode, but then that bytecode is loaded by the JVM, you know, and we see the JVM and the Kotlin or Java compiler as being peers, you know, of one another. They exist at the same level, you know. So anything the Java compiler knows, we expect the Java virtual machine to know. The clues in the name, okay? So the fact that stuff that the Java compiler knows is not known by the virtual machine, that causes all kinds of problems, you know? So we have a leaky abstraction, yeah? So can Kotlin help us? Of course it can, you know, otherwise there wouldn't be any point to this talk, yeah? So it can help us in 4 ways, and let's just run through them quickly. So the first of all is that we get rid of these hideous bounded wildcards. They're gone, okay? So what do we have instead? Well, we have declaration site variants. What? Okay, so let's say I'm going to write my own list implementation. well, I can have an interface that contains the read-only operations, the operations where we're only pulling out t's and doing stuff with them. And I can indicate that to the compiler by saying out t. So whenever I declare my type parameter, I can use the out keyword to tell the compiler I'm only taking things out, and it will only let me take things out. By the way, taking things out to put them into a lambda, that's fine, okay? So find first and find all, those are just fine. And then we can go the other way. So let's say I want to have like a sync. So I want to put the operations for writing into another interface. So I can do that, and I can say int. So now I'm saying that I'm only going to be passing values in. I'm not going to be pulling them out, okay? So I can have both those interfaces, and then of course the same concrete type can implement both of the interfaces, yeah? So I can have a my list that implements the read-only list and the write-only list. And then the same questions can be asked, yeah? So by the way, I'm not giving people an opportunity to answer these because I've got no way to get the answers back. And there's a delay on the video, so it would be incredibly confusing, But one thing that you might enjoy doing is going through the slides for this talk afterwards and trying to answer the questions before you go on to the next slide. It's a good indication of how good your generics knowledge is. So we can write the same, we can answer the same questions in Kotlin so that the same kind of rules apply, but now hopefully it's a lot easier to understand. So instead of having to have my bounded wildcards, which I would have before, I've now got my read-only list interface, and I've got my write-only list interface, and so on. And hopefully things are a little bit more intuitive. Hopefully things make a little bit more sense. Yeah. So that's the idea of declaration site variants. Of course, it does depend on you giving good names to these interfaces, and naming is hard. Yeah. But hopefully you can get past that, So declaration site variants to me makes a lot more sense than using your bounded wildcards. But let's say, we can't create the interfaces, we're working with other people's types and so on. Well, then we can have used site variants. So you see here, whenever we're declaring our function, we can use the in keyword, yeah, or we can use the out keyword, So we can use the in and out on the type parameter whenever we're declaring our functions, yeah. And that does the same job as again, as the bounded wildcards. So an interesting example of when you might want to do this, and this is the example that everybody gives, is let's say we've got two my lists and they don't have read-only and write-only interfaces, but we want to take 10 items out of the first and put them into the second. Yeah. Well, then we can use the out keyword on the first and the in keyword on the second. And then you can also do constraints and generic types. So we can say t:employee. Yeah. So that effectively adds an upper bound. And you can use the star to mean of unknown type. So that is the equivalent of the question mark in that case. And again, these work the way you would expect. So much for our wildcards. What about reification? So here's a practical example of reification. Let's say we have a function that takes a list of any, and we want to filter it. So this is a generic function that takes a type parameter t, and what we want to do is we want to select only those t's. So if you look at the code, we're going to loop over all the things in input, and then we're going to do a type check. So we're saying, okay, if item is of type t, where t is the generic type, we'll then add it to the output, okay? So will this work? Well, having built it up to this stage, you're all, of course, expecting me to say yes, but the answer is no, because Kotlin compiles to bytecode and runs on the JVM, so we're still working with non-reified generics. So it won't work unless we give some help, okay? So what we can do is we can say to the Kotlin compiler, look, I want t to be reified, okay? So every time I call this function, there will be a value for t. It could be string or customer or date or whatever, yeah? So I want a different version of the function, yeah? But of course, that's not something that bytecode or the JVM supports. So the only way that we can make that work is by inlining it, okay? So we can say generate a new version of the function for customer or string or integer or whatever, but then inline that at the call site, yeah? So if we do it that way, then it will work. So just to prove the point, here's some example code. So you see here, I've got my main function and I create a list of numbers and strings. And then we're calling example 1 and example 2. And example 1 uses filter by type for int, whereas example 2 uses filter by type for string. So in example 1, we only want to print out the numbers. In example 2, we only want to print out the strings. So here's our filter by type. And this is what it gets converted to. So if you haven't done it already, in IntelliJ, there's a really nice feature where you can take your Kotlin code and you can say generate bytecode. And then you can say, please reverse engineer that as Java. Okay, so I really recommend this whenever you're trying to get your head around a weird feature in Kotlin. You know, so whenever Kotlin is performing some kind of magic for you, yeah, well then take the code that you've written, get the bytecode view, and then if you can look at raw bytecode and understand it, well done. You know, otherwise hit the button on the bytecode view that will reverse engineer it as Java. Okay, and then you'll be able to see what's going on in Java terms. So you see here we've got our two functions, example 1 and example 2. So just going back, remember that example 1 we were filtering by int, example 2 we were filtering by string. Okay, and that was our filter by type function. So if you look, the code for filter by type has been embedded in both example 1 and example 2. Okay, so the loop has been turned into a while loop using an iterator object. So we're saying has next and next, and we're pulling back a value. And in Kotlin terminology, we were using the is. In Java, that becomes the instance of course. But note that in example 1, we're now saying instance of integer. And in example 2, we're saying instance of string. So what the Kotlin compiler did was it reified the function and then inlined the function call, you know. So it's really, really good to be able to have that. And this is something that I do all the time, yeah, because I'm a huge fan of generics because I came up through C++, you know, where templates, as they call them, are used all over the place. So I'm fairly comfortable with generics. I really like them. So here's a good example of where I was using it the other day. So I was using Spring Boot, and actually I was using Spring Webflux, you know, so their new reactive API for writing RESTful services. And here I'm just sending a GET request to a URL. And I'm going to get back some JSON, yeah? And this JSON is going to be a list of order or customer or employee or string or whatever. That's the T, okay? So T here is the type of the thing that's coming back from the server as JSON. So for each customer, let's say in the JSON document, I want to create a new customer object. For each order, I want to create an order object and so on. So in general, I want to create a whole bunch of new T's. Yeah. So I wouldn't be able to write this code generically unless I had reification available to me. So I can declare T as being a reified type, and then I can inline it. You know, so this is the way that you'll use reification all the time, you know, in your day-to-day coding. So is Kotlin better? Of course, you know, otherwise I wouldn't be doing this talk. Yeah. So just to finish off, where might we go in the future? Okay, so we have barely scratched the surface in Kotlin and in Java of where we could go with generics. Okay, so let me show you a really interesting feature. So one of the places where they're really pushing generics to the max is inside TypeScript. They're doing lots of really fun stuff in TypeScript at the moment. And one of the things you can do is mapped types, okay? So we all know what the map function does in functional programming. You're doing a transformation, same kind of idea here. So what we're doing is we're going to take an input type, T, and we want to generate a new type by iterating over the properties of T. Okay, so whenever you see the square brackets here and the P and key of T, we're iterating over the properties of T, you know, the members of T, the slots of T, however you prefer to think of it. So if I just said here P and key of T, TP, well, then I just get a type which is absolutely identical to the original. Yeah, but you see here what we're doing is we're saying read only. So I'm adding the read-only modifier, okay? So let's say T was customer and customer had 5 properties, yeah? Well, then we're going to get a new type, which is the same as customer. It has the same 5 properties with the same name and the same type, but now if they weren't read-only already, they are now. Okay, so I can get a read-only version of a type. Or I can go the other way. Yeah. So let's say I know that the input type has one or more read-only properties, and I want to take those off. So I could declare a mutable t, and then in there we can iterate over the properties of t, and then we can take off the read-only flag if it's there. Okay. In the same way, let's say we wanted to have a partial version of a type. Okay, so in TypeScript, we can use question mark to say this property is optional. You know, this field doesn't have to be there, and it'll still count as an instance of this interface or type. Yeah. So what we can do is we can loop over the properties of t, and we can make them all optional with the question mark. Or, yeah, we can take that off. We can make them all mandatory by saying minus question mark. And then it starts getting weird, okay? Because we can change the type of the property if we want. So I'm sure everybody on this call has had the horrible experience in Kotlin or Java or Scala or whatever, where you've got multiple trees of objects. So let's say you have a well-designed customer type, but then you're receiving customer information from the UI or the RESTful service or whatever, and everything's going to be strings, yeah? So you have to write stringly typed code. So you had your customer class with 5 well-typed fields, but now what you need to do is declare a new class the same as customer, but where everything's string, you know, and that's where you're going to load the data from the UI or the RESTful service or whatever. Yeah. So it's going to be a terrible, terrible maintenance nightmare if you have like 100 entity types and you want 100 string versions of those. Yeah. Not if you generate them. So you see here, I could say stringify of customer, and then loop over all the properties and change the data type to string. Okay. There's only one problem with that, which is that properties in JavaScript and TypeScript can be either fields or methods. Okay. So if there were any methods in the type, they'd be changed to string as well. Don't want to do that. Yeah. Well, the good news is that in mapped types, you can do conditionals. Yeah. So again, I can loop over all the properties, but now I can say, okay, yeah, if the type of this property extends function, then leave it alone. Okay. So just convert it to whatever it was originally. Yeah. Otherwise, convert it to string. So let me just show you that in action. So you see here, I've got a person type and a customer type. So person is going to have name, age, and married of type string, number, and Boolean. And customer is going to extend person and add a method called make order. And then I've got some demo functions. So I can test a regular person. Of course, I can change the name to Dave. But let's say I've got a function that takes a read only of person. So I will be able to pass in a person object, but I won't be able to change the name. You know, I'll be forbidden from changing anything in input. But what I could do is I could call test mutable, yeah, because test mutable takes a mutable of person, okay? So if you like, I've converted away the read-onliness, yeah, of the person object, and now I'll be able to go in and change it. Or I can write a function that takes a partial customer. And then here's an interesting example of stringify. So let's say I've got this variable called customer, which is of type stringify customer. In other words, it has the same number of properties as a customer object, and those properties have the same names, but now they're all of type string, okay? So you see there, I can go through and I can now set them all to string values, okay? The only problem is that for the make order function, it's now a string as well. Oops, okay? So what we want to do is we want to say stringify fields. So now what it'll do is it'll say, okay, this type is the same as customer, and all the properties that are fields, well, their data type has changed to string, but all the properties which were methods, well, then they've been left alone. So they will have the same parameters and return type as they did in customer. Yeah. And then there's a little demo there to just call those functions, and this is the output that you'll get in the browser. Yeah. Just to call your attention to one nice little bit here, you see I can say partial person. And this is an object literal in TypeScript. So we're saying, okay, this is an object that has a name and an address. Okay, sorry, a name and an age even. Yeah, and it's not a person because it's missing the married property, but it is a partial person. It's like a subset of the person type. So I can call test partial and pass in my partial person, and that will work just fine. Okay, so you can go out and play with this now. And there's a term for this This is called type-driven development. Okay, so this is the new TDD. Okay, so you're all familiar with the old TDD, test-driven development. There's the new TDD now as well, which is type-driven development. Yeah. So if you want to get into this, the most accessible way I'm familiar with is start playing with a little bit of TypeScript. And there's this library called the TS Toolbelt, and it contains a whole pile of these types built in. Yeah. But of course, it's even more fun to go out and write them yourself. And they're continuously adding new functions to do this kind of thing in TypeScript. So you see there, one just got proposed just the other day. So there's one where we're doing this kind of thing in tuples, and that will be coming to the next version of TypeScript. So what have we learned? So we've gone through 3 different acts. So first of all, we've seen what the problem is in Java terms. Then we've seen how Kotlin makes your life a lot easier. And then we've seen what's possible, the ways that the JVM languages could be extended in the future. So just to sum up, first of all, generics deserves a lot more respect than it gets. Okay, so generics is a programming style in its own right. It's at least as complicated as OO and FP. So whenever you're teaching other people to program, I strongly recommend you spend as much time on generics as on OO and FP. Give it the respect it deserves. And then FP works perfectly with generics, but it's complicated with OO. Flat classes are fine, inheritance is not. And then Kotlin makes it much simpler. Kotlin learned from the mistakes of Java and the bounded wildcards and so on. So declaration site variants and use site variants and the in and out keywords and so on, they're great. So if I was teaching somebody to code in the JVM, I'd go straight to Kotlin if at all possible. And then you don't need reification. Java has proved that. So you can do generics without having reified types, and it'll still be incredibly useful and productive. However, reification is very convenient. This ability to say new T and so on, well, that opens the door to all kinds of other possibilities. Yeah. And then finally, there's a lot more to generics than you think. Okay, so what we think of as generics on the JVM, that's only like chapter 1. Okay, there's a lot more fun things we could do with generics, and perhaps some of these will get added to the JVM in the future. Cool. So that's my show. That's all the stuff I wanted to cover. So the slides will be made available after the talk. Please feel free to have a look and to reach out to me if you have any questions.
Okay, there are no questions. Oh, yeah, okay. Just been popped up into the slide. So thanks.
Yeah, so there is one question if I answer it, which is, could TS-like features be implemented in the JVM without runtime reflection? That's out of my league, but I'm going to say yes, because TypeScript at the end of the day just generates regular JavaScript. Yeah. So if the TypeScript transpiler can do it, then I assume that the Java or Kotlin compilers can do it as well. Okay. So I'm not completely sure, but my instinct would definitely be yes.
Okay, cool. Thanks so much, Garth. Super interesting. I think I have to rewatch it again because there's so much to learn from your talk. Thanks so much. So that's all. I want to thank again Matt, Nico, and Garth for being with us today. I want to thank my co-organizer Guillermo, who again handled the streaming flawlessly. Amar organized everything with the speakers and with our managed all the QA. Thanks so much for tuning in. I hope you enjoyed it, the talks, and the recordings are available here on our YouTube channel. So spread the word to your family, colleagues, friends, whoever be interested on social media. I can already confirm there will be a next event next month. Will be on Wednesday on August the 5th. And again, subscribe to our YouTube channel and check out our Meetup page for all the info. That's it. See you next time.